Hi, you guys. In this video, we're going to go ahead and talk about an acid-base solution called a buffer. And so we're going to talk about what makes a buffer solution, how do we calculate pH of buffer solutions, how are they different from regular acids and bases. So let's go ahead and get started. So before we talk specifically about buffer solutions, we're going to do a little bit of background information first of all and talk about what is called the common ion effect. So we kind of talked about this a little bit with KSP and those solubility problems. But basically what we first need to think about is when we're talking about the common ion effect, we're talking about a solution that has a weak acid. So in this example that I have down here, I'm talking about my weak acid, HF. And that weak acid is not just in a solution by itself. So maybe we have another salt that's dissolved in that solution. So like maybe say that I take sodium fluoride and I take that solid sodium fluoride and I dump it into my solution of HF. Well, when I take sodium fluoride and I dump it into a solution of hydrofluoric acid, which is mostly water, that's going to break apart into sodium ions and fluoride ions. Well, the ions that are in sodium fluoride, the fluoride ion specifically, is common to the fluoride ion that is in HF. So when we start to do the common ion effect and those types of problems, basically when we're dealing with our ice tables here, we're going to have a starting number here and we're going to have a starting number here. So it's going to be like those KSP problems where we started with numbers that weren't always zero over on the right side. So that's the deal, is we're going to have a number that starts right here because we have fluoride ions in the solution already. So what you need to know about that is if you have fluoride solutions in the solution already, and Q is products over reactants. By the way, these are all aqueous solutions, so they would all be included in our K expression. Q would become greater than K because my products would be greater than my reactants. And if Q is greater than K, then my reaction is going to shift to the left. Basically, what we need to know is if you have a common ion dissolved in an acid, what that means is that it is going to basically limit that forward reaction from happening. You're going to have a lower percent ionization. Okay, so that's kind of a key thing right there, is if you have something starting in this common ion that doesn't start as zero, then that's going to lower the percent ionization, how many molecules can break apart in the solution. You're going to have less hydrogen ions. You're going to have less fluoride ions produced because they were already there to begin with. So talking about the fact that a common ion lowers our percent ionization or a percent dissociation, we did this problem, sorry, this first one, in class on Friday. And when we calculated the percent ionization for the acetic acid solution that has a concentration of 0.1, oh, quick reminder, we're going to need this. Our Ka for acetic acid is 1.8 times 10 to the negative fifth. We calculated the percent ionization and we got a percent ionization of 1.3%. Okay, so since we did that in class on Friday, I'm not going to make you redo it right there. I just want us to put that percentage there to remember what that percent ionization is. And now we're going to compare it to if we have a common ion. So let's look at this. It says now we're going to go ahead and calculate the percent dissociation of a mixture that contains 0.1 molar of acetic acid and 0.1 molar of sodium acetate. Now the sodium acetate is NaC2H3O2. And we're talking about this being dissolved in acetic acid. So the common ion here is acetate. Sodium will be a spectator ion. That means that this concentration is going to be 0.1 instead of 0. My H3O concentration will be 0. Notice in this equation, I did include water just to show you a different way that the equations can be written. So if we do include water in our acid equations, then instead of it being H plus over here, it'll be H3O plus. But H3O plus and H plus, that means the same thing basically. That's what we're going to be negative logging to calculate the pH. But let's go ahead and calculate that percent. So if I get 0.1 plus X here and plus X here minus X here, I'm basically going to have, and my Ka value is really small, so my X values are going to, my X values that I'm adding and subtracting, I'm going to be able to cancel out. So I'm going to have an X there for H3O plus, and then I'm going to have a 0.1 here for my acetate ion instead of X. So when I go ahead and I solve for X, if I know K, I get 1.8 times 10 to the negative fifth. I get not X squared on the top this time. I get X times 0.1 and then divided by 0.1. So my 0.1s are going to cancel basically, and X is 1.8 times 10 to the negative fifth. So when I go ahead and calculate my percent ionization, I'm going to get 1.8 times 10 to the negative fifth is my X value over my initial concentration. My initial concentration is 0.1. And then I need to go ahead and multiply that by 100. Which gives me a percent ionization of 0.18. Nope, just kidding. I missed a zero. Let's do that over again. 0.018%. Okay, so let's just look at that. I want you guys to compare these two numbers. So without the common ion, the percent ionization was 1.3%. With a common ion already dissolved in the solution, the percent ionization is 0.018. So having the common ion lowers the percent ionization. Okay, that's important concept for you guys to understand. So now with that, now that we understand what is going on there, let's go ahead and talk about what a buffer is. So a buffer is a solution that basically has what we just talked about. It has the common ion effect. It has a weak acid, and then it has something else dissolved in there that has the common ion, which would be like the conjugate base of that particular thing, right? So like HF, looking back just at our example, we had HF, we had H plus and F minus over here. So HF was my weak acid. It has to be a weak acid or it doesn't work. And then my conjugate base of that weak acid, we had numbers, we had starting concentrations of both of those things. So a buffer can have that, or it can be a weak base and a significant quantity. I mean, you don't have to worry too much about like what that means. You're always like, if you're given a buffer problem, it's always going to be considered a significant quantity of its conjugate acid. So an example of that would be like NH3. And then if I have water, I'll have NH4 plus and then OH minus. So what we would have in that buffer situation is we would have NH3 and we would have NH4 plus. Those would both have starting concentrations that weren't zero. And what happens is, and we're going to write a bunch of equations in class next time, but what happens is because you have both of those things, it's able to neutralize anything that you add to it. It can neutralize an acid that you put into the solution. It can neutralize a base that you put into the solution. So really buffers are solutions that resist their change in pH. So our blood is a really good buffer. Like our pH, the pH of our blood has to be a specific amount. And if it goes too high or too low, then, we can't live that way. So it has to be able to like absorb all kinds of different things and not have the pH change very much. So let's go ahead and talk about, now we can do calculations of pH values with buffer solutions where we have not just a concentration of the acid or the base, but of the conjugate as well. So there is an equation that goes with buffers, and that equation is given to you. This equation right here is called the Henderson-Hasselbalch equation. This is calculating the pH for buffers only, okay? We can't use this to calculate the pH of anything else that we've been doing up until this point. We can only use it to calculate the pH of a buffer. So we have to be able to recognize if we have a buffer, first of all, and then be able to use this equation. So a couple things we need to notice here is we need to notice that when calculating the pH, we're going to be calculating something called the pKa. Now, when we calculated pH, it's the negative log of H. So calculating pKa is calculating the negative log of our Ka value. Now, if we're dealing with an acidic buffer, then they'll give you the Ka value. But if you're dealing with a basic buffer, they're going to give you the Kb value. But you still have to plug Ka into this equation. So we do have to remember this equation. Kw equals Ka times Kb. Kw is 1 times 10 to the negative 4. Just kidding, negative 14. And then, so Ka times Kb. So if I'm given my Kb value, I'm going to have to plug that in and solve for Ka so that I can go ahead and plug it in over here. It has to be Ka every single time. If you are using this equation, it has to be Ka, no matter if your buffer is considered to be acidic or basic. You have to plug in Ka. So we'll do that here in just a second. And then this equation is shown specific to an acidic buffer because we've got Ha on the bottom, and then we've got A minus, which is the conjugate base on the top. That's what it would look like if we were dealing specifically with an acidic buffer. But another way to think about this equation is if you're taking the log of, it's always going to be whatever the base concentration is, whether it's a regular base or a conjugate base, over whatever the concentration is of the acid. So let's take a look at this example. We'll do 2 examples of buffer calculations. Oh, I do know that I skipped the example higher up on the page. We're going to come back to that. So we're going to deal with this example first, calculating the pH of a solution that's 0.5 molar NH4Cl and then NH3. Now, these are already mixed together, and these are the concentrations that are measured. Okay, so first of all, I'm going to see this, and I'm going to realize that's ammonia. And I've told you guys to memorize ammonia and know that that's considered a weak base. Now, the conjugate acid for ammonia is NH4+. Okay, so that's considered the common ion, and chlorine is not a part of the thing. Okay, so that's my weak base. This is considered to be my conjugate acid of NH3. Now, the other thing that I did not type in here is since the buffer is basic, they would be giving you that Kb value, which is 1.8 times 10 to the negative 5th. That would be given. So if I want to use this equation to calculate the pH of a buffer of this buffer solution, I first need to calculate the Ka value. So I'm going to do Kw divided by Kb. So that would be 1 times 10 to the negative 14, and then divided by 1.8 times 10 to the negative 5th. Okay, that gives me 5.56 times 10 to the negative 10. So that's my Ka value. Now I can go ahead and plug things into this equation to calculate the pH. So I'm going to go ahead and do the negative log of my Ka value, which was 5.56 times 10 to the negative 10, and plus the log of the base over the acid. So this is where people just need to make sure, or you guys just need to make sure that you're plugging everything into the right place. Really identify what's the basic part of this and what's the acidic part of this, whether it's a regular or a conjugate. Okay, so NH3 was the base. And in this equation, the base concentration goes on the top. So 0.3 is going to go on the top. And in this equation, the bottom is where we put the acid concentration, whether it's a regular acid or a conjugate acid. That's where my NH4 comes in. So 0.5 is going to go down here on the bottom. And plug all that into your calculator. Make sure that you're good with your negative logging and plus log of all that stuff. Put it into your calculator correctly. You should get a pH value of 9.03, which makes sense because I'm dealing with a solution that is a basic solution with the conjugate acid that's there. Okay, let's go ahead and go back up to the example higher up on the page. We'll do that one as well. So in this example, we have, we want to calculate the pH of a buffer where I have 50 milliliters of 0.5 molar. This is sodium acetate mixed. Keyword, when you see mixed, you automatically should think, I mean, it's kind of a bummer, but you automatically need to think these are mixed together. So concentrations are changing. So I'm going to have to do M1V1 equals M2V2. Okay. When you see solutions being mixed together, and it's being mixed with 25 milliliters of 0.25 molar acetic acid. Okay. So this is my acid, and sodium acetate, the common ion that is in sodium acetate is going to be acetate. Sodium is going to be a spectator ion. This guy right here, acetate, is the conjugate base of acetic acid. Okay, so what I need to do is I need to find these concentrations, the new concentrations after they're mixed together. Okay, so let's go ahead and do for my base, which is my C2H3O2 minus, I have to do M1V1 equals M2V2. So the molarity, just to find the new molarity, because I'm mixing it with other stuff, right? So my concentration is 0.5, V1 50 milliliters, and then I'm looking for that new molarity. I've got to add my two volumes together, so 50 plus 25 is 75. So that molarity that I get is 0.33. I need to remember that that is the concentration that I calculated, the new concentration of the base. It is the conjugate base. Now I need to go ahead and do the same with the acid before I can go ahead and plug it into my buffer equation. All right, I'm going to do M1V1. I'll do this pretty quickly because we've done this before. M1 is 0.25. My V1 of my acid is 25 milliliters. I need the new molarity and the second volume of them mixed together, 75. Okay, so that molarity is 0.083. And since that was acetic acid, that's going to be my acid concentration. K value. Ka would be given. It just so happens in these two examples that the Ka for acetic acid and the Kb for ammonia are equal to each other. That's just a coincidence in like the strength of each one of them, but it's not the same for every weak acid and weak base. Okay, so now I'm going to go ahead and I'm going to plug this in to my buffer equation to calculate the pH. So pH equals pKa plus the log of, and I'm just going to remember it this way, base over acid, whether it's conjugate or regular, okay? So pKa, that's the negative log of Ka. Since they gave me the Ka value, I don't have to calculate it separately like I did with the last one because it was given, because it's an acidic buffer, plus the log of, and then the base is 0.33. And my acid is 0.083. So that's really the hardest part of this equation, is just knowing which one to plug in as the acid and which one to plug in as the base. So you need to read your questions carefully. You do get 5.34 as the pH of that solution. Makes sense. It's an acidic buffer with acetic acid and the common ion acetate. And the last thing in this section, this is going to make Wednesday so much better because we're going to have all this done and we can just write equations on Wednesday, is this type of question. You might see a question where it says like a student or whoever needs to prepare a buffer that has a certain pH. Okay, so in this example, it says which acid, and we've got these 4 acids, chloroacetic, propanoic, benzoic, hypochlorous. Which of these 4 acids? And we're talking about if we have these acids with their conjugate base partners so that it makes a buffer, which one would make a buffer with a pH of 4.2? And we're given Ka values of all 4 of these acids. So here's what we need to know. We need to know something about buffers. If you make an ideal buffer would have the same concentration of acid and base. And the reason why that is because if you have the same concentration of both, then it has the same ability to, to neutralize both acids or bases if you put them in the solution. So if I look at this equation, my buffer equation, pH equals pKa plus the log of, and it's base over acid. If my base and acid all have the same concentration, I basically get the log of 1 over here, right? And if the log of 1 is 0. So we're looking for something, if they're asking us, which acid could I use to make a buffer with a pH of 4.20, the best way to figure that out is to take the pKa values and compare them. And you want to pick which one has a pKa value closest to 4.20. So if I go ahead and if I'm finding the pKa, it's the negative log of the Ka value, right? So I can go ahead and negative log all of these Ka values and I can get the pKas. So when I negative log my chloroacetic acid, I get 2.87. When I negative log propanoic acid, I get 4.89. When I negative log benzoic acid, I get 4.19. And then when I negative log hypochlorous, 7.5. So looking at all of my pKa values, I want to pick whichever one is closest to 4.2. And so benzoic acid is the closest one. So anytime you're asked, what acid should you use to get a certain pH value, you're looking for one where the pKa and the pH value equal each other. And then that would be the best acid for that. Okay, that's it, you guys. We're going to do the equation writing for buffers in class. So I'll see you guys on Wednesday. We'll practice doing buffer calculations, and I'll see you then. Have a good night.